Hello, good people. Welcome back. I'm finding there it is. So these first two examples, first two videos was about using long division to rewrite the integrand. We use long division whenever the numerator degree is bigger than the denominator degree. Whenever my rational function is top heavy, maybe long division can help us rewrite it, make it easier for us to take the antiderivative. But when I look at 3 and 4, that's not the case. As a matter of fact, 3 and 4, this is a bottom heavy situation, meaning that the degree of the bottom of the denominator is bigger than the one on top. The degree of the bottom is bigger than the one on top. So how do we get around here? And so here, we're going to rely on something from Algebra 2 called completing the square. Completing the square means that if I have some kind of quadratic setup, I can somehow rewrite it into something that looks like this, right? This is a quadratic and this is a quadratic. The difference being, and maybe I should put an A here. The difference is that one of them, I have a factor squared. Here, I don't have a factor squared. And let me tell you why we want to change it like this. Some of our antiderivative rules, like this one, like this one, like this one, are some of those rules where if you recognize the pattern, oh, that's going to be arctangent, or this is going to be arcsine, or this is going to be arcsecant, right? And so if we're able to rewrite it and make it look like this rather than this, then that's going to maybe get us to one of these shortcuts that we know and love. So let's come back over here. I want to make the denominator go from standard form to vertex form. How do I do that? Well, first of all, I group the x squared term and the x term. So those two are going to be together. The plus 10 is on the outside. Whatever I do inside of the parentheses, I got to do the opposite on the outside of the parentheses to keep it balanced. And what we do is we take the middle term, this term, we cut it in half, and then we square it. So I'm going to take 6, and I'm going to cut it in half, and then we square it. Now, if I do that, that would be 3 squared. That would be 9, right? Now, I'm going to tell you why we're doing that. Maybe I should do that in another color. We're going to add 9. Middle term, the x term, coefficient, cut it in half, and then square it. So I'm going to add 9 on the inside, but I just said whatever you do on the inside, you got to do the opposite on the outside to keep it balanced, right? Because if I add 9 and subtract 9, that means that I didn't really change this expression at all. But why do we do that? Because this is now factorable, and it is factorable, or is factored to x plus 3 times x plus 3. On the outside, I can get plus 1. And x plus 3 times x plus 3 is really just x plus 3 squared. And so what I just created is an integral that looks like this. So what I'm claiming is if you were to square out x plus 3 times x plus 3, and then add 1, you would get this denominator. But why do I want it like this? Oh, because it reminds me of the arctangent antiderivative. And so I'm going to come back over here, and I'm going to do a little u substitution. I'm going to say u equals x plus 3. That means du equals 1 dx. And I'm sorry, I forgot the dx here. So I have a dx. I can replace it with a du. And then I have x plus 3. So this can become u to the second power plus 1. Hey, this is the setup I need for arctangent. And so my answer, or tangent inverse, if you will. So tangent inverse of u plus c would be the antiderivative. And if I go back into the world of x's, that would be tangent inverse of x plus 3, because we said u was x plus 3, plus c. And this, my good people, is the antiderivative. How did I do that? By completing the square. So completing the square means I'm trying to change the way that the quadratic denominator looks. I want to take it from standard form into vertex form, because if I take it into vertex form, it might connect with one of these antiderivatives that you memorized for arctangent, arcsine, and arcsecant. Let's try that again. Um, something, and definitely want to do number 4, because number 4 gives us a situation where we have to be very careful. The denominator is not just the quadratic, it's the square root of the quadratic. That's okay. I'm going to factor out the quadratic. I'm sorry, I'm going to complete the square on the quadratic. But I do notice something. This time my leading term is negative, and it works best if you have a leading term that's positive. So I'm going to take that negative and I'm going to take it out of this. Yes? Oh, I didn't take it out. And I also didn't group my things. So I'm sorry. I need to group. And now I'm going to take it out. So I'm going to take out that negative. Negative. With the parentheses still there. So what's left if I take that out? Well, that would be x squared minus 8x. The minus 15 is still there. So just to recap, if I distribute this back inside and I minus 15, I'll get the inside of this square root, right? Okay, now I'm going to do the rule that allows me to complete the square. So the rule that allows me to complete the square says take the coefficient of the x term, so that would be negative 8, cut it in half, and square it. So I'm supposed to take negative 8, which is negative 4. I'm sorry, negative 8, cut it in half, that'd be negative 4, and then square it, so that's going to give me 16. And then I'm supposed to balance it out on the outside, right? Just like I did over here. I introduced the 9, and then I balanced it out with a minus 9. And so I introduced a plus 16, so I'm supposed to balance it out over here. But the problem is I have this negative in the front. And so really, I didn't introduce a positive 16. I introduced a negative 16. And so I need to balance it out with a positive 16. Do you see why? When I distribute the negative, I'll get negative x squared. Hey, that's what I have there. Negative of a minus 8x, that's positive 8x. Negative of 16, which when I put it with plus 16 is going to go away, and then I'm left with negative 15. Why did I do this? Oh, because I'm able to now factor this into x minus 4 times x minus 4, which would leave me with x minus 4 squared. And then on the outside, I'm just going to be left with plus 1. Maybe I should do that in green. Plus 1. Wow, that was a lot. Okay, so that means this is equal to 1 over the square root of negative x minus 4 quantity squared plus 1. Or would it be nicer if I reversed it and I said 1, positive 1, minus x minus 4 squared dx? Because now, when I look at this, what do you think the u is in this situation? If you said x minus 4, you'd be correct. That means du is going to be dx, and this, my good people, is going to transform into the integral from 1, the integral of 1 over the square root of 1 minus u squared du, and this is the antiderivative of arc sine plus c. And then I can put it back in terms of, by the way, I'm writing arc sine and I put the inverse, I'm sorry. Either write arc sine of u or write sine inverse of u. Don't do both like I just did. And then that's going to lead me back to arc sine of x minus 4 plus c. This is the antiderivative that I'm looking for. If I'm claiming that if you take the derivative of this, you're going to get this integrand, which is this original setup that we had. Using completing the square can help you rewrite the way a quadratic looks so that maybe it matches with one of the arcsine or inverse trig function derivatives or antiderivatives. If you don't remember how to do completing the square, that's something we can talk about in class or in tutorials. We can remind you of that, as well as if you don't remember how to do long division, we can do that in tutorials as well.